I guess. Whatever happened. Great that you're back and we are back.
I have a question on the slide.
Yeah.
Are you taking questions during the talk?
Sure, we can do that.
What is accuracy here? I mean, what is being
It's the angular distance between the target. Like we had the whole study set up where we recorded ground truth data using a Baikonur and Optitech system to track the finger's position, and then we compared what the deep learning model would spit out and what the ground truth was, and that we did for the re-implementation one, and that was basically a root mean square error for what the first paper gave out, and then our paper, and then from this is a 9% drop, and that's a 45% drop between those two papers.
Do the absolute numbers mean anything, or it's only important the relative change, the drop of 9%, or does 14.19 actually have some?
Oh yeah, if you yeah, it's basically if you just look at that's a squared error, so then but if you look at the mean absolute error, that's 11 degrees different.
The unit is degrees. Okay.
Yeah. Oh yeah. Yeah. So yes, the difference between the ground truth is 10, and here it's 11.5, and then the ground truth difference is on absolute mean absolute error is 17 and 33.
So I mean, maybe not in this context, but you know, these 10, 11 degrees is very big.
Yeah.
You're walking up a hill.
That's correct.
In this context, is it big?
Well, it depends on the user interface, right? If you only have two states, it's no problem. If you go for every angle, then yes, that's a problem. And then the next question becomes is the underlying trend jumpy, or is it more like continuous offsets between the two, right? There's lots of this in the paper.
Okay.
Okay, and then actually, yeah, that's basically the next slide. It's like, okay, what do we open with this? Like, if we have such technology, and then rotating objects in space might be one cool thing, but there's a whole range that we published in another paper, all of the things that we could actually do. So rotational input for like actually making pie menus possible on touch screens. Scrolling would be one, list menus, and then the 3D manipulation, joystick input, zoom in and zoom rotation, and tilt all in one point, and picking from a color menu, making the pencil width different depending on how you basically, this is what you would have from a real pen, but now this you can have a simulated finger as a pen, and if you get the rotation from that, you can make the width of the pencil depending on this. Okay, so this was the first outlook. It was like, okay, cool. If this is what we actually could gain from every commoditary touchscreen device in the world, if we have this capacitive screen or this capacitive matrix, because we know under the hood they all work the same as soon as we go away from resistive screens. And then we look at this, okay, cool. So this is the first step. What else can we do? And one of the simple things is like, okay, cool, we can make an algorithm or a model as well that determines the difference between a palm that faces on the screen. That's something that we typically use to reject input, right? We have palm detectors. That's like, okay, this was not a finger, it was not a touch. We don't want that. And a finger. And then you seem like, oh yeah, but palms are all big, so that's easy to detect. And yeah, you might be right in its end state, but really tricky is the state where the palm just hits the touch screen and tries to understand, okay, could this shape now be a finger or a palm? And then of course this makes the first step in this line of work on trying to understand, because now we have the finger orientation and we know, okay, that's palm input. And then we know that we can do palms and fingers. Then we can even do two fingers or more than two fingers. Like how many fingers can we actually do potentially? And then this is a video of left and right thumb. And with this capabilities, we can just think, oh, what's possible new interaction that we can enable, or what enabled can we bring back? And that's actually exactly this first scene. It's like, okay, we draw with the right finger. That just seems seems reasonable. But then we have this other finger, and the other finger then can pop up the context menu. So like there's this one side is like, okay, we need to detect that, and that's possible, that's cool, so we can understand, but then we also like look at what can we actually open with this? Can we open new possibilities with that? And then in the paper, we actually look at not only the 2 thumbs, but we actually look down to all 10 fingers. That's really hard, especially because then we look at finger sizes, and like the more finger we include, obviously, the more the accuracy drops. But I think with 10 fingers, we're still at 60% of accuracy. Yes.
I'm just a bit curious about the, like, oh, you report the error. So for example, did you also do that varying by age? Like,
no.
No, okay.
No, we just use the random sample.
Okay.
Probably like 30 people, most probably like that. And then what we typically do is a chain validation and test split. And then on the generalizing model. And then I believe this paper also had an extra study where we looked at the usability of using 2 fingers, right? So with that totally different, totally new set of people, giving that this drawing application and asking them how did it work for them? Yeah, because then if you can easily overfit to like the 10 or 20 participants that you have, but then by generating the 3 splits plus this extra validation study, you really ensure that there's an underlying generalization in this model. So now we looked at, okay, we can understand fingers and hands, and then the next step would be, okay, we can also go into time series. Just need to, yeah. So now we're like, okay, we know understanding of knuckles, but now we do long-term short-term memory in order to also understand gestures that are possible. And that was another question.
Yeah. So when you are using these sort of deep learning models,
yeah,
you know that you need a lot of data.
Yeah.
So how because collecting data, that much of data from people is always difficult. So how did you manage to collect that much of data? Are you using all the frames? For example, like when you touch, you use individual, like when you touch, we know that these touch screens work at about, I don't know, 50 hertz or 100 hertz, and then you get
way less, but yes.
Yeah.
Especially if you draw the capacitive matrix, because internally you need to go through the kernel, you need to hack Android, and then you need an I2C bus to look at the debug interface, and then you're down to like 9 to 12 frames.
Oh,
but yes.
Right, okay.
Yeah.
So you use each individual frame?
Depending on what we did, yes.
Right. And the other question is, how did you test it? Because I assume, this is an assumption, I'm curious to hear how the data reflected this, because the way these fingerprints are different, heavily based on the way you hold the phone.
Mm-hmm.
So is there a way that you can leave one user out for testing and still the system works? So is it within the user that it
No, we never used within user. That is, yes, you can do that, and lots of researchers do that. It's like, oh yeah, we train for this one user, it's 90%. It's like, it's great.
Yeah.
But what about the other basically 100% of people on the planet? No, they all generalized across multiple users. All of this, they have between, I would say, the lowest number for this was like 18 people, and I think we went up to like, and one paper was like 35 people. So that's the range of data we collected, and then we did this 3 splits where we trained on most of the time like 60%, and then we tested and did hyperparameter tuning with another 20%, and we have another 20% for like just testing at the end. So that's the common approach to have a generalized model. Yeah,
because that's a very challenging problem, isn't it? Because probably most people have different ways of grasping the phone. So if it still works, it's very
Oh yeah. I think I'm not a fan of user-based models, because then you have this like investment. Every user needs to train for like, most of the studies we do is like 1 hour of data recording, all of these, like, so you have like, I don't know. I know for the first paper I showed that I know it was 500,000 samples from roughly 20 people. And if you think about that, it's like everybody needs to sit down for an hour to train their user-independent model. Nobody wants to buy that phone, right? So we want generalizable models. Otherwise, there's no point. It's like, oh yeah, you get your phone. It's like, oh great. We know that from the iPhone, right? It's like takes like 3 minutes to scan your face. It's an investment. That's okay. It's for security. But if I'm telling you, you need 1 hour in order to use your phone because otherwise you can't rotate stuff or you can't do some input, that's not possible. Yeah. Okay, so we explored this dimension of like, okay, now we go into this LSTM version and stacking multiple together and like look at this. There's similar model from a CNN structure, but then on top there's this time series model. And that's really now all around the finger. But from the finger, that's only so little of the human. And then it's like, okay, how do we get the rest? And normally what we do to get the rest, we buy a motion tracking system because that's the cheapest, or that's the best out there. It's super expensive. And then we looked at one of the papers actually. It's okay, how can we actually go with the sensors we actually carry with the phone as well? Because the phone has quite a number of sensors. So a rear camera, front camera, IMU, depth camera, and the touch sensor. We know the touch sensor, we can get a lot of the information out there, but what about the other ones? And what we wanted to, yes.
What is IMU?
The inertial measurements using, to like get accelerometer data.
And depth camera?
Yeah, the iPhone depth camera. It gives you distance, the point cloud of the distance to the phone. Yeah, there will be, I will scroll into, that would be, stop here. That's basically the front-facing depth image. So all of the new iPhones, that's what they do for security measures to like not be fooled by images, is there needs to be a face visible and there needs to be some depth, because otherwise you're just holding a picture of myself in front of my phone, and that would be really bad. Happens to a lot of Samsung phones. But what we get out of the depth camera is basically, the projector is maybe not the best, but basically here it's a bit lighter than here, and that's the difference in depth for the torso with respect to the holding phone. That's the depth camera image that we get here. Okay, but if we actually combine all of these, so we have the IMU, like trying to understand accelerometer data, and gyroscope, we get the orientation of the phone. Then we know from the touch we can simulate arms. And then, as I said, from the depth camera, we can get out the torso. From the torso, we get the orientation towards the phone. If we have the phone as a root and put everything into this root, we can rebuild the world around that. And then we have the camera facing into the world that scans the world and understands like how is the camera moved towards the world. If we now center this back to the phone's perspective and put the human on the other side, we know how the phone actually moves through the world. So we get that idea, and because we also have height estimation, we also get and can animate characters, especially if we combine all of these different elements. We know how the phone moves, we know from the touch screen how the hand moves, we know the torso movement, we know the head movement from the front-facing camera. And then we put all of this together in combination with an inverse kinematics model. We get some decently looking character animation that you could use on the go without spending $50,000 to $100,000 on a Vicon and Opticheck system. And I think that's quite nice if we think about applications on the go.
So I missed how you managed to get the position of the character in the room.
A tracking of objects in the world.
Sorry?
Basically tracking of objects in the world. There's quite a number of toolkits that can do that.
What I'm trying to understand is the only sensor, the phone, or you have some?
Yeah, it's the only sensor.
And so the phone is tracking objects, but not just the person, but other objects in the room.
It's using the front-facing camera to check the face and torso, right? The upper body that's visible. And we use the rear-facing camera in combination with inertial measurement units to understand how the phone is moved within the world. To basically do triangulation in the world.
So there needs to be some wall or some object. If you were just in a flat plain in the desert, in the sea, you can't triangulate this way?
You can based on IMU data, however, it has a drift. You need physical landmarkers to stabilize away the drift that you have from the sensors that's typically there.
Okay.
But yes.
Cool.
All right. And that's really about like having the user understood now, and then we go into this next perspective in like actually understanding the world around the user and trying to understand what does the user manipulate. And one of the things here I'm like quite inspired, because that's also the time when I really started to look into HCI, is like how do we actually interact with objects and tabletops, and how can we now enrich this third dimension on the screen? The screens are quite interesting because we have so much visual input, but then there's no haptics, right? There's nothing there. But we typically, over the last couple of thousand years, we had objects that we manipulated, and we are quite worse with our fingers on how to do that. So how can we fuse those two together? And there's a lot of research out there on doing that, but all of them vanish basically if you look at them. Just like just 99 and then 2000, 2011, 2012. Really try to understand this in the first place, but then something hit the market that is the capacitive screen, and they got rid of all these tabletops, because these tabletops are all infrared based. They scan through the surface. There's a back projection, and the back projection then can also take the infrared image of the objects, and then we can do high fidelity scanning of the objects, and that is really great. But as we've seen from the finger tracking, today's touch screens, they're really coarse, and they're not a lot of information, and that's a huge problem. If you think about how this actually looks like, and there's some text, there's some play figures, like one of the examples, we have a D&D game, and we have these tags, and we place these tags on today's screens, and this is the tag number 2, is the tag that we would get out from scanning a 2x2 centimeter tag. Right? That's really low in resolution. And then the question becomes, okay, how can we do this? And like, because this doesn't help in enabling a D&D game on everyday touchscreens, and this might be a tablet, might be a tabletop. And then we use things from astronomy and biology, and it's like really a super resolution technique. And in this case, we do multi-stacking geometric super resolution. So basically, over the course of 37 frames, that we, as we already alluded on, scan with like 9 to 12 frames per second. That then sums up to 2.5 seconds delay. But let's wait for that part. We stack them, 37 frames, we align them, and then what we get is actually an resolved image number 3. And that's the tag that represents more number 1. And if we actually then apply thresholding, we can use typical April tag detectors. And that is an April tag, something used in robotics to understand how robots move to the environment with optical scanning. If you now slap on an April tag detector, and if you would have one on your phone, you can scan this tag, and it would tell you, I think it's tag number 8 in April tag 16H5. And then we can do object detection on today's capacitive screens. And that's really the first step on bringing back all of these old ideas from tabletops back to today's devices, because based on this vanishing technology of bulky infrared sensors, that they all went away. And we today don't have this capabilities of tracking different objects. And just in a showcase here, a bigger card that we could place on our screen, and then we have the low resolution one and big one, right? So 6 centimeters in width for the showcase of this. Then we have this tag on the lower right, lower left. And then we actually want to do something like this, lots of small objects on the screen, and if they're also tracked, and when we know where they are, put labels on and enable touch as well at the same time. And this is really the idea that we brought in from these older papers to like, okay, how can we really revive this? And the problem with the approach I just showed you is this 2.5 seconds of delay. That's a huge issue. Right, it's an investment every time you place a figure on the screen. It's like, okay, let's wait for 2.5 seconds. Then I could do it manually on the screen. There's no point in doing that. So we want single frame detection. And there's a paper out there that does single frame detection. However, one of the problems is you're restricted in market limits, because we can train, as we did for the fingers, one set, like let's say 20 to 30 markers that we train, build a deep neural network to go from here directly to, oh, this is number 5. And that they show that works not for these markers, but for another marker set, but it works with a decent accuracy. But really the problem is we're stuck to the markers given, but the problem is like we want to give designers all of the ideas like how to design these footprints and like make others and enable others to design footprints and design these tags themselves. So with the next paper I want to present, we're also tackling this idea that we talked about earlier real quick in the discussion. It's like, okay, we need to collect all of this data to pre-train this, to train these models. And to get around this, one of the approaches that we use is a general adversarial network to simulate capacitive marker. I'm gonna run you through real quick to this. What we have is we have the template. That's basically the marker the designer designed, right? High resolution footprints. They're basically only black and white, just to rastering. You can basically go into Illustrator, design a tag, a footprint, whatever the footprint looks like, a star, or these kind of April text. You have these templates, and then what we have to make our paperwork, we have ground truth recording again, right? Because we need some accuracy at the end. But actually what we're after is this simulation. So we want to go from the template to the simulation, and the simulation shouldn't be much different to the recording, because otherwise, again, we lose generalizability. So these two need to be the same, because if we train only on simulated data, there's a high chance that if the simulated data is not accurate, that it won't work in the real world. So let's look at,
Why do you need simulated data at all to train? Because you don't have enough data?
No, I don't want to record data because that's the same problem. If I tell you, yes, you can design your own tags, but then you need to record data, and you need an OptiTrack, you need a device, you need to sit down for 2 hours or 5 hours, or in our case, like more than 20 hours of data recording. That's not feasible. Nobody's going to do that. We want fully simulated data to get around on this. So the idea is designers gets a tag, and then we have capacitive image, and then we have a generator in the middle. That's our simulator. And then we actually, for this, we have simulated data, right? We have simulated data. We can train a recognizer based on simulated data. And that can be all done in one go without user input. We only need those tags. And then we can train a recognizer, and that recognizer gives us the marker ID and the orientation or the rotation, because that's kind of interesting, because especially if the tags, if they're square, it's also important to get the rotation. And then we can feed real-time data into the recognizer and get this. Yes.
So the idea is that anyone could come up with a design for a tag, and then the generator would be able to train the recognizer on that tag, and you don't need to have like specifically trained the recognizer beforehand.
Correct.
Right.
Yeah. Okay. Right. So the generator should simulate all tags in the world, and because no recognizer can recognize all tags in the world, you say like I need chess, so I need 64, I believe, or 60 figures, or I need 1,000, doesn't really matter. So you design 1,000 tags, simulate 1,000 different tags with different parameters. So there's a bit random in there, and then you build this train a recognizer, and then you have this ring tag. And this lower step only works if this generator is properly working.
All of this is done on the device, or it's done?
No, that you do before you deploy. You can do that on any GPU server. And there will be a slide in a second from the part that you actually put on the device. So the idea, you have the tag with the simulated capacitive images, and then there's some encoder decoder network in the middle with some skip connections. I don't know if you, let's skip that for now. And then we have the recognizer, and the recognizer also has a model, and that model is fixed. We showed up to 60 classes. There's basically no loss in accuracy for marker, and basically no change in rotation error. So you have these 2 branches that fade out to predict those 2. And this recognizer, this is exactly that part that you actually, when you have a recognizer and you have this frozen recognizer, there's nothing to train. You take that from your GPU server or from your server farm, wherever you want to train it, and you take that model, reduce it to some 8-bit optimization and deploy it on a phone, so it actually also runs fast. And then you have your new observation. That's what comes in from the touch screen. It gets into the recognizer, and the recognizer tells you what it is. And then if you do blob detection beforehand, you can do multiple, so you crop patches around all of the blobs, and then each of the blobs get classified independently from each other. And that enables tracking multiple objects on one device without actually recording any data and getting around that. So how does this look like? Now we do 3 different tags on the train. Bigger one, smaller one, and then you can basically here see the rotation gain, and you see also which tag it is. It's tag 8, and one of the pixels is 6 millimeters, and for this one is tag 14, and one of them is 4 millimeters. And I would argue, and especially for the small ones, it's quite hard to come up with what this is, right? And then, of course, looking at all of these other things that we had like 10 years or 15 years ago, it's like what's possible. It's like, okay, we build all of these tangible applications that we've seen in the past. It's like, oh, a tangible museum where you can explore different objects, just place them on. You have the haptics of this object, and then you get additional information. We had already the D&D game that we can build then. I can do smart home applications here, multiple tags on the screen to operate different. And then we could have just giving back control, like we always do, like give this tangible bit back to this radio station. All right. And with this, we kind of understood, okay, we need to know, if we think about new interfaces in the world, we kind of need to understand, okay, what is the world and what is the user state currently? And then I want to give one example and how I envision these 2 things combined and work together. And one of the examples, or the example I want to give, is one that I already highlighted a bit earlier, where we think like, okay, if we know more about the world, more about the user, then we can enhance voice interaction. And for this one, we built a gaze-aware voice assistant. And we used similar techniques from the paper where we scanned the body. We actually used, again, the rear-facing camera and the front-facing camera to understand user and the world. So the front-facing camera understands where's the face, and then gets a face raycast, a forward vector of the face itself. We could do eye tracking, of course, and there's a lot of papers that do eye tracking based on RGB data without using any markers and any infrared cameras, the typical eye tracking. But for the sake of this demonstration, because it only makes accuracy better, but doesn't really do anything else, from an interaction point of view, it still will give us this feeling, how would such a system look like. We decided on a more stable forward-facing ray from the face. And then by knowing how the 2 cameras align to each other, we can project the ray that goes into the phone out of the phone on the other side. And that's the right side image. We see that the ray goes into the world. And that's actually where the person looking into the world with a device in the middle. And it could be, in this case, it's an iPhone, but you can also think about this just a head-mounted display. At a Google Glass, for instance, that has a camera that faces the eye or the face and one that faces into the world. And then what's really interesting, we can make a sentence like this actually happen. Because when does this open has no meaning to current voice assistant. There's no way they will understand what this means. But in so many cases in this, like, hey, when does this place open? What is this? Like, you don't know what it is, and that's a problem. You can't identify what it is. Or you can identify it and you're standing in front of Starbucks, but there's like 100 Starbucks in the city, and there's like, oh yeah, when does Starbucks open? And it's like, yeah, here's like a list of Starbucks, and that's actually what happened on current systems. But if we have such a gaze-aware system, and we do scanning of the world, and you see that actually there's some labels that give you an indication of what are the things that you can look at, because we did also implement scanning of the world, understand some of the objects, so there's some businesses. And for a debug interface, obviously, right? In the real world, you would just have your phone that scans both, and you have your voices. And then you can substitute, or the system can substitute, oh, well, yeah, from the gaze, I know what this means. And this is actually the Oakland Fashion Optical. And then a lot of information is pass into it, and you can build way more rich interactions. You think about the kitchen example in the beginning, it's like how to address this one light. And actually, these are the examples, and we also built them like spun up from it here. There's a shopping example. Like typically, you go to the thing that if you're lucky, it has a price tag, and you can compare prices. But with such a gaze-aware system, you can not only query, for instance, here for like, what's the price of this? Okay, you get the price of the black sofa, but then you can do similar things. What's the price between this and this? Now you can combine phrases, and you get actually response, because this is clear. And right, it's like this armchair. So this, like, while I look here, it's like, okay, this armchair, and while I look there, it's the other armchair. The system can query, because it knows the two armchairs, and can query the price and actually do the math for you and give you the price difference between the two. That's one where we can like clearly enhance and make more a dialogue system that we have today. In the other case, we can actually reduce language and reduce burden to the system. Because if we know what we're looking at, we can reduce lots of the things like, hey, put the volume down, or hey, put the heating down. It both could work with the key down, depending on where you're looking. It could be, okay, the thermostat, I'm looking at it and I say just down, and it's clear it's the temperature. And the other one is like, I'm looking at the TV and it's the volume that goes down. Same for on, right? So this is one of the visions that I would portray, how we can have a systems for the future. And then to like close a bit and use the last couple of minutes to like really understand, okay, where were we going from this? And one of the limiting things currently I feel like is all of the systems or ideas I showed so far is in the digital space. And I can query a voice assistant for an opening time or a price difference. That's clearly digital. And I can manipulate my lights. And in a way, it's only an API call. And I would say, yes, there's some physical thing happening. Lights gets turned on, but really it's a digital signal via an API that makes this happen. And where it becomes really interesting, I believe, if we combine these assistants to build such dialogue systems, if we combine them with an embodiment, if we give them a form in the world to actually do stuff in the world. Because then we can look at something like this. If we have two robotic arms, kitchen example, right? We have two arms and we want collaborative cooking. If we have this embodiment, we can now potentially, right, future vision, tell our system to like chop the onions, for instance, right? And then, okay, there's lots of the things like how onion chopping works and the mechanics, and also on like all of the robotics parts. But from a human interaction perspective, we now could, if we think back in this like idea of like using human communication to make an interaction with the system happening, really here's the idea. It's like, okay, I can tell my system like, yeah, please go ahead and chop the onions. But on the other hand, we then see, because we have world understanding, on my system knows maybe I want to do pasta, and I already have the pot on the stove, and it's boiling, but also my doorbell is ringing. So I'm like rushing to the doorbell to get my package, because my Amazon delivery is really important. But then my pot is overheating, and now we have this context awareness of the system that is like, oh, I know he's outside the room, but I also know the pot is overheating. So the system can actually support me while I'm not even there. And I think there, this collaboration between systems and human becomes really interesting in the future. So with the next steps that I'm going to take is really looking into this dialogue system, because onion chopping for us is very simple. But if we tell a system how to chop onions, it's not so simple. It's like a really hard task. And then not only is it a really hard task, most probably I'm chopping onions differently than everybody else. So I do slices first and then the other side, and then I want tiny pieces or bigger pieces depending on the dish. So there's a lot of options that you can do to actually give your system. And to build such a shared control and giving away this control, we need way better mechanisms than we currently have to just ask for a price tag or an opening hour. That's really simple things. But if we have a system perform things in the physical world because there's no reverse, right? The onion is chopped, that's it. So we need this negotiation process, and how do we actually want that? To what degree do we want to give away control? And at one point, the system can actually tell us that's not the right way. And that becomes really tricky from a human perspective, because if we think in other domains, operation theaters, most tasks, or there are a number of tasks that can be performed better than a doctor. But at what point is the doctor okay with the system telling him, just like, do you know what? Just stop, I'm gonna do that. I have my arms, I know I'm trained on this routine, and I can do it better than you. Like, how does this negotiation process look like? That's totally unclear, I would say, today. But that's really interesting, because we will have that. We will, in the future, we will have these operation theaters where we have remote operation. Also in this kitchen example, right? Very, very simple, and like if something goes wrong, it's not a big deal. But still, we can practice and understand this negotiation and process in the future. And with this, I would also want to conclude how I think the next generation of computing systems could look like, and how I believe that artificial intelligence really meets the human, and how we need this dialogue between them. And I presented 4 areas. The first one was like, we really need to have more understanding of the human as more context for the system to make decisions and stir this negotiation process. We need the system, but also understand the world. What do the human manipulate in the world? We need good understanding of the world as well. And I showed one example of how such a artificially empowered system could look like, and what this could enable in the future. And then I highlight a couple of challenges and where future trends might go towards. And with this, I think I hope I kind of inspired my research goal to like enable humans and machines to learn and accomplish tasks better together. Thank you very much.
Thank you. It was a really interesting talk, and we'd be happy to take questions now. If you're on Zoom, please, you could unmute yourselves and ask a question. And we have also some questions from the audience. So
I'll just put Zoom up here. Okay, cool. And then there were questions. Yeah, please.
Yeah, I've got a very quick question. So at first you were saying that like compared to uncrafted features, using a more like learning CNN approach was better. What are the drawbacks? I'm guessing like the size of the model and possible like attacks, but is it like a concern, or do you think that?
I think for building these interactions, we often have this, that we overestimate what we think is important. And by this, we reduce accuracy, right? So if you do handcrafted features, like, this feature won't be important, let's skip it. And that's dangerous. And that's what the deep learning model isn't doing. It considers all of them. However, the downside of considering all of them is also it could consider noise in the background, right? And this is something we need to like fundamentally understand better from an AI perspective. But then all of the things I showed is I'm not developing new deep learning techniques, right? So all the things that I applied are things that are out there that come from NIPS, NeurIPS, or all of the different machine learning conferences are currently booming, and really trying to understand, okay, what can we take from what they learned and apply this in an intelligent user interface to make new systems, and especially explore what's possible in the future and how does this feel to the user, right? Such that voice, a gaze-aware system. Without building it, there's no way to understand it. So even though, yes, there might be drawbacks in it, probably there's way to attack such a system today. This was the first time that we can actually explore that. And I think that's the first step, like from an HCI perspective. And then, yes, there's like explainability and all sorts of like trying to understand what parts of the model, what parts of the image the model is actually looking at. All of these things, like, is it actually looking at the bounding box, or is it looking at corners where we know there's background noise in the capacitive image, or like looking in the sky to determine whatever. right? All of these things like icebergs on yeah. Other questions?
Maybe on Zoom? No.
No, on Zoom, there's no questions there. Yeah.
I have a provocative question.
They're the best.
You showed the sort of the tables.
Yeah.
That are now that kind of got supplanted by these touch screens, right? And I'm wondering if you could talk about what aspects of your research will survive whatever the next technology is, right? I mean, at some point we're going to move beyond these touch screens, as you've shown. They're quite, I mean, I don't know, let's just presume, right? What aspects of your research can be carried forward to, you know, are somehow general enough that they could apply in a different mode, the way you took things that applied beyond what happened with specific infrared tables?
I would say, since I often try to go for this human approach and like trying to understand how humans would do that with each other, and this approach, no matter what the technology that enables it, this approach, besides humanity changes drastically, will survive, right? Whatever new technology either supports the same thing or it will vanish for some time, but then most probably some other technology will enable that back, because the idea of pointing is so old, but we do that like, I mean, also if you study pointing, it's like already like really children in their like very young age already do that. So I think as focusing on these things, while they might vanish for some time, they will come back. It's the same for like a mouse. There's no expressiveness for your fingers, right? It's like two buttons and like an XY coordinate on the plane. But the idea of the richness of our fingers will not vanish. So that will always stay. So I think these type of like understanding the user, there might be the technology change, but the interaction paradigm at the end, how do we want this interaction, that I would say would stay. The technology changes, yes, absolutely, of course.
Thank you. Let's see if we don't have any more questions. Let's thank Sven again. And if you want to be connected, please reach out to me or to Sven directly. Thank you, Sven.